Okay, so our next speaker is Assaf Shocher from Weizmann. He will talk about visual retargeting of natural images using an internal GAN, and this is a work with Shai Bagon, Isola, and Michal Irani.
Okay, thanks. So this is joint work with Shai Bagon, Isola, and Michal Irani. So the challenge of retargeting refers to changing the size or aspect ratio of an image, and there are plenty of reasons for why you would want to do such a thing. For example, creating a visual summary or a thumbnail. Perhaps you want to change screen, for example, for a cell phone screen, or create some artistic effects or synthesize graphics, for example, for gaming. And there are many possible ways of doing retargeting, and first we'll review the most trivial ones. So probably the most trivial way you can retarget an image is just scale it. But in this way you would lose some resolution and objects would be distorted. Another thing you can do is just cropping, but then you would lose some valuable information. There are many works that do retargeting using non-uniform scaling. So the typical thing would be identifying important information in the image and then maintain its original size while scaling the other objects in the image. Another possibility is the seam curving, in which you remove or add these seams of the least valuable information in the image. But this has only local considerations and it can't add or remove new elements in the image. The bidirectional similarity states that all the patches in the target image supposed to also be in the source image and vice versa. But the bidirectional similarity lacks the large-scale consistency. Recently, there's been the work of non-stationary texture synthesis, and this can also be viewed as sort of texture retargeting. So what we have there is some non-stationary texture, and then using a GAN, self-supervision, and style loss, it is extrapolated to twice its size. But this is only good for just single scale for a texture, and it can only do it for exactly twice the size of the original image. So what is a good retargeting? Having this input example, we would want to change its size, for example, downscale it, but we don't want the local elements to change its size too. So in this particular example, you can see that the windows maintain the original size, we just have less of them. We may also want to enlarge the image, so in this case we will have more of the elements in the original image. We may also want to change the aspect ratio in one direction or in another direction, and generally what we're looking for is to preserve various element sizes and relative locations. So here's our approach to it. Having some input image X and the wanted target image Y, so the bidirectional similarity says that you want all the patches in X to also be in Y and vice versa. But we suggest a stronger requirement. We say that we want to do distribution matching, so that the distribution of patches in the source image will be as close as possible to the patch distribution of the target image. And we want this to exist for all possible scales. Lastly, we want to preserve the relative locations in the image. So in this example, you want the watermelons to maintain their position at the top of the image. Reformulating these three requirements to one general requirement would result in this requirement. We want to do local distribution matching of patches in all scales. And we can formulate this as a conditioned probability with respect to the relative location in the image. So, how can we match distributions? So, over the past few years, there is a great way of drawing examples out of a learned distribution, and of course I'm talking about generative adversarial networks. But can they be applied to natural image patches? So about a year ago we presented our own work called Deep Internal Learning, and in there we explained that in a fully convolutional network, every pixel of the output is actually just a function of the corresponding patch in the input image. This is why actually just one image contains tons of data, and we actually demonstrated how we can train a convnet just on one single image. So incorporating this and combining with GANs, we get what we refer to as an internal GAN. That is, we train a GAN on a single natural image. So let's see how the InGAN works. Having some input image, we feed it into a generator, but we also feed it with the desired scales that we want to retarget to. Then we'll get what we're hoping is the retargeted image, but to make sure that this is what we get, we're going to feed it into a discriminator. Now, this is a patch discriminator, so it doesn't produce just a scalar, it produces a map, and every pixel in the produced map corresponds to a patch in the output image. So for example, if you have this white pixel somewhere, it means that it corresponds to a patch that is very likely to be drawn out of the learned distribution. And similarly, if you have some black pixel, it means that this patch is probably non-valid. So we're going to train this discriminator and generator using the labels, which are either just a full map of ones or a full map of zeros. But of course, we also need a real example, or maybe real examples, if we want to be able to train the discriminator. So our real example is just one example, and it is just the original input image. But you have to keep in mind that even though it is just one example, it has tons of data inside it because it consists of many patches. So basically this is it, this is our GAN, but there's still one major problem, and this is a common problem for GANs, and I'm talking about mode collapse. And apparently internal mode collapse is a thing. So for example, imagine what would happen if we didn't have the guy over there or the bull next to him, or maybe what if they switched places. So basically the discriminator wouldn't have any problem with this, because this is a patch discriminator, and every patch in this output image is still valid and likely to be drawn out of the distribution. So we have to make sure somehow that we are keeping all the information. So what we do is we take the output image and we feed it into a decoder. Now the decoder tries to reconstruct the input image again, and we're just using a regular L1 loss to make sure that it is able to do this. Now the logic here is that if you are able to reconstruct the original input back again, it means you have no missing information in the output image. So our general loss here is just a combination of the GAN loss and the reconstruction loss. Now let's see how the generator works. So the generator has a unit architecture and these 6 res blocks in the bottleneck, but a very important layer to notice is the resizing layer. Now this is a parameter-free layer, but it does expect as inputs to get the desired scales. And during training time, this would be just random scales, so it trains to all possible scales. And in test time, we feed it with the desired scale that we want to retarget to. Now let's see the discriminator. First, let me just remind that this is a patch discriminator, so that every pixel in the map corresponds to a patch in the input image. Now this is a multi-scale discriminator, so when an image is fed into it, the first thing we do is downscale it. And then we downscale it again and again to all possible scales. And then we have a different unit of the discriminator for each possible scale. So these are not shared weights. These are like very small, but a lot of discriminators. And they produce this bunch of maps in various sizes. So the next thing we do is we upscale them so that they all have the same size. And then we take a weighted average. Now the weights controlling this weighted average are what makes this discriminator an adaptive discriminator, because we get to control and decide which scale matters the most. And the way we do it is that during early stages of training, most of the weight is concentrated in the coarse scales, but then gradually, as training progresses, it shifts to the finer scales. So this way we get this coarse to fine routine when doing the training. Lastly, in the architecture, we need to discuss the decoder. Now, the truth about the decoder is that it is just another instance of the generator, only with scales taken as the inverse of the first instance of the generator. And the reason here is that this challenge, as opposed to, for example, domain transfer challenges, is actually an automorphism. We're not changing domains, we're just changing the scale of the image out of this continuous space of possible image scales. And the great bonus we get here is that the second instance of the generator actually also performs retargeting. When you think about it, you see that the inputs that it gets are in various sizes, but the output is always in the same size, the original input size. So this way we get to train the generator more for retargeting, but this time, instead of using a GAN loss, we have the much more stable L1 loss, and this stabilizes the entire system. So you may say that this part of the architecture is actually like an autoencoder, but we're using the same encoder again. So this is not an autoencoder. Here in Israel, we can say that this is an autoencoder. Okay, let's see some results. So given this input image, we retargeted to get this output, and you can see that the corn cobs aren't just stretched, but we have more corn seeds added to it. And if we target it in a different dimension, then you see that we actually have new corn cobs generated. Now, interestingly, no two corn cobs are alike, so it's not just duplicating. What we get here is that the new generated corn cobs are actually drawn from this implicit corn cob distribution, and they consist of corn seeds, which in turn are drawn from an implicit corn seed distribution. In fact, training in GAN1s allows to apply it to all possible scales just in real time. So we are able to produce these videos of varying scales that we are able to retarget to, and you can see how new corn seeds appear when changing, and then also how new corn cobs are born and then eliminated, and you can see that the transition is smooth. This is because we train it for all scales, and then it needs to fit continuously to all the possible scales. Let's see some more examples. So these are examples related to multiple textures, and you can see in this fruit example here that we have textures in various sizes. We have the watermelon size, we have the smaller fruit size, but we also have the fruit boxes scale. So we have new fruit boxes appear or cancelled during this retargeting. Here's another example, this time with the windows. We have several types of windows here, and we managed to keep the global structure of the building, but just change it in a way that makes sense while keeping the sizes of the windows. These are two more examples related to adding and removing large-scale elements from the image. And you can see how new penguins, for example, are added and removed from the image in a smooth way. So there are really some nice advantages to this method. And the first one would be that we only have to train it once on a single image, but then we're able to produce all the retargeting we want in real time. And second, this is totally unsupervised, and we don't need any data. The only data we're using is the input image itself. And we can handle multiple elements in various scales, and this refers to multiple textures too, and it is in general very flexible and very suitable for natural images. Okay, so we ran some comparisons to other methods. Now, these are two results you've seen before of InGAN. So here's how the bidirectional similarity looks like. And you can see that locally it looks pretty well, but it doesn't have large-scale consistency. So for example, you get these watermelons at the bottom of the fruit stand, and this is obviously not the place they should be in. Sim carving really distorts natural images with many objects, and the non-stationary texture synthesis, it can really just handle one scale of textures. So it handles the melons pretty well, but the smaller fruit are kind of smudged away. Here's some more comparison, and in this comparison you can see that the bidirectional similarity produced something that more or less looks like just taking a crop from the top part of the image, and the InGAN produced something that I would consider as a really good visual summary of this image. It only has one carrot. Here is another example. So here we changed the aspect ratio, and you can see that the bidirectional similarity again looks locally okay, but it has one bird missing, and it brought this branch to the top of the image from somewhere. And InGAN kept the 3 birds, and it kept their relative position in the image and their original size. Okay, here are some more examples. These are marching soldiers, and you can see how more soldiers are added. Don't be frightened. You can see how more soldiers are added, and this includes new soldier faces. So if you look closely, you can't look closely now, but if you look, Mike? Hey? Okay, so, what, Mike? Okay. So if you look closely, you can see that all these faces are not just duplication of faces. Again, we have these faces drawn from an implicit face distribution. Here's another example. This is a sushi menu, and you can see how new items are added or removed from the menu. And this demonstrates the principle of local distribution, because you can see that the area of nigiri dishes produces more nigiri dishes, and the area of rolled sushi, fotomaki, produces more rolled sushi dishes. So here's the carrot you've seen just one example of before, and you can see how when the carrots grow, new carrot texture is added. It's not just stretching, and as it grows more extremely, then more carrots are added or removed. And the basic thing to notice here about the distribution is that the ratio of carrot to wood is actually preserved along all possible scales. Here's another example of the Capitol building, and you can see that new floors are added to the main tower and to the size of the building. And it is also possible to retarget faces as long as you don't do it too extreme. So, for example, here you can see that Elon Musk's eyes and mouth maintain their original size while the global shape of the face is changing. Okay, so our take-home message would be that this is not just about retargeting. So the most important thing to notice is that local patch distribution is the best way to describe an image, and we actually see it as the DNA of an image. And if one wants to produce a brother or a sister to his natural image, the best way to do it is using this DNA. Another thing is that we just showed that it is possible to train a GAN on just a single natural image. And we want to state that one of the key ingredients to be able to do retargeting is using this multi-scale discrimination. And lastly, seeing retargeting as an invertible problem and using an invertible generator is also very important for the success of retargeting. So, thank you. And I just want to mention that we're going to have our paper uploaded to archive very soon, and we're going to have our code also available on GitHub. Thanks.
Questions?
You introduced your work working on multiple elements, but only that they appear more than once in an image. How does it work if you have one element appear only once?
So basically, if we only have one element in an image, so you're going to expect to get a good retargeting, but in some cases you wouldn't have this element duplicated. It really depends, because if you have no patches in the image or nothing in the distribution that implying to a patch that sees both instances of this object, it could be hard. But if you're talking about for example, two different elements in different parts of the image, then it's still possible. You'll get retargeting.
And another question, what is the minimal size of the patch it works on?
Again, sorry?
What is the minimal size of the image that is on the input layer you trained in net on?
What is the size you asked?
In pixels.
Oh, the minimum size. Okay, so we usually use sizes of 256 square. So relatively small images are faster to train on, and it makes it easier. But We haven't tried a minimum size. We know from prior work on super resolution that for deep internal learning, about the size of 40 over 40 pixels is still possible.
Thank you.
Thanks.
Great work. Do you imply that the retargeted image, there is only a single one retargeted image for each input image, or are there many different images that are the retargeted of the same input image?
So there are probably many possibilities, but I suppose they would be close to each other. Since I guess if you take the exact same setting with the different random initialization and run it over again, you'll get something that is slightly different. But the conditions that we made actually make it, actually determine it to be that all the possible solutions would be rather close to each other. We have a more tight bound for it.
Other questions? Okay, so let's thank the speaker again. So we will have a coffee break now till 11:10. I just want to mention that we will post all the lectures on YouTube and we will mail you with the details.